So our next speaker is Joseph Norby from Carnegie Mellon University.
Hi, cool. I'm Joe Norby. I'm a PhD student in the robomechanics lab at Carnegie Mellon. And one of the things that we're interested in is making robots that can go anywhere in the world. And today I'm going to talk to you about why I think tails might be, or tail-like appendages might be something that can help robots do that. And some of the kind of features that we're looking at, such as robustness, and as I'm going to talk about, efficiency. In particular, this has kind of been a bit of a limit to putting robots out in the real world and having them last in a real environment outside the lab for a long period of time. And you have some robots that are designed to be very robust, but take a lot of actuators and weight to do the things that they want to do. You have some that are more focused on this very efficient task that can go for a very long amount of time on a charge, but they might not be able to do the kind of more robust tasks. And then you have some in the middle. And what we're hoping to do is see if tails can kind of break this trend and both add this kind of additional robustness, but also, as I'm going to talk about, increase the efficiency. So there have been some prior work. This is a work by Dr. Amir Patel, adding tails to a robot to improve its dynamic capabilities. And it was able to turn around and maneuver these turns more tightly at high speeds. In addition to dynamic capabilities, these kind of limbed systems can improve balance. So this is the Atlas robot a while ago with these two tails, or arms, I guess, that help it provide this balance. And then researchers have also started to look a little bit about how you can reuse reaction wheels to kind of mitigate this extra energy that comes from having this mass on your system, because you're adding weight, and that usually hurts your efficiency. So we want to know, to what extent can we intelligently actuate a tail to kind of mitigate this extra energy consumption that comes with adding this mass? And also, is there a certain tail or robot that is better suited to a tail in order to kind of minimize this additional cost? And the way we look at this is with kind of this nested optimization structure. So we have an outer loop that just selects a tail mass for our motor, or sorry, for our robot, which in our case is the Ghost Robotics Minotaur. It's a quadruped. And then this outer loop feeds that tail mass into this inner loop trajectory optimization, where it generates a gate. In this case, we're doing periodic bounding gates. And it tries to find the most energy optimal gate possible for that particular robot and that particular tail. In this case, the cost function that we're using is energy consumed per unit distance, not cost of transport. We do not normalize by mass, because if you use your overall cost of transport metric, just adding tail mass to the system will decrease your cost of transport. And that's a little bit misleading, so we don't include that. We're just looking at for how far can we travel for a certain amount of energy. Here's some of the optimization details. If you don't care about optimizations, that's fine. Just look at the pretty animation. But this is what the inner loop the optimization is doing. It's running a direct collocation method with a number of constraints and variables. It's in the Frost framework, which is a optimization and simulation toolkit designed by Ayanga Ireed and Aaron Ames. So if you want to know more about that, talk to me about it. But what do we learn when we do this? So we looked at letting the optimizer simply just add tail mass to the system. So we start with an initial tail mass of 0.5 kilogram, and the optimizer eventually then selects for 0 tail mass. So that means that at least for our system, it seems more energy optimal to just not have a tail at all. However, if we change the parameters a little bit, and instead of just adding that mass to the tail, we replace it, we transfer it from the body. So if you took some sort of payload, for example, your battery, computer, something on your actual robot, and move it to the body, or sorry, from the body to the tail, then we see that the optimizer selects to move as much of that mass as possible. And for reference here, we have, this is if you have 0 tail mass, and then this line here is if you also remove the extra weight that you need to have the motor and the mounting for the tail. So we see here that in this case, if you were able to have this much mass in your actual tail, you can move more efficiently than if you didn't have it at all. So in conclusion, If we kind of leave this total mass unchanged, we are able to, at least for our system, improve the overall efficiency. But more importantly, we've kind of developed this optimization framework that we use to kind of handle these questions of both design and control. So moving forward, we're hoping to scale this for other morphologies, to other robots rather than just ours, expand it so that we don't have to specify, for example, that it is a bound, and also look at, rather than efficiency, can we be more robust over kind of varied terrain so that these robots can be in the real world. And with that, I'll take any questions, and I wanted to especially thank Ayanga for his help setting this up. The simulation.
So your results say that you should transfer as much of the mass to the tail as possible, and it says that it's going down. And if you were to interpolate that or extrapolate, I should say, you would say like, oh well, as you know, the whole mass of the robot should be a point at this tail, which to me it seems unintuitive. Like it must go up at some point.
So we had to stop it because So what you're seeing here is each of the outer loop evaluations for different tail masses.
Yeah.
And so it would just hit an error because it would try to do as much as it possibly could.
Why do you think that is? Do you think that's a simulation problem, or do you think that's a real effect that you want to have this essentially oscillating inverted pendulum on top of your robot?
So I think it's leveraging the passive dynamics of essentially keeping that mass vertical. And so then the legs are what's moving kind of the mass around. So as you're taking mass out of the body, you're kind of separating it from what the legs have to do. So the legs don't have to work nearly as hard. So it's essentially just isolating it from what the legs have to do.
Does adding the mass also have a moment of inertia, or does it become
it's a point mass?
A point mass. So
yeah.
Could this possibly be with like you're getting rid of your moment of inertia and just turning it into a point mass? Could that be?
That could be something to look into and possibly adding an inertia there. But yeah, it is a point mass.
Okay.
Okay, let's thank Joe again.